All right, let's just jump right in. What if you could build one single model that explains, well, everything? I'm not just talking about one little piece of the puzzle. I mean the whole shebang. From the tiniest switch buried inside a computer chip, all the way up to the massively complex system of our entire planet. It's a huge, ambitious idea. And today, we're going to break down how you'd even start.
And this quote, it just nails it, right? This isn't about some abstract thought experiment in a lab. The whole point is to build models that actually reflect things that exist in the real world. It's about figuring out how reality, with all its messiness and complexity, actually works.
Okay, so where in the world do you begin if you want to model all of reality? Well, you have to start small. I mean, really small. At the most fundamental level, we're talking about the building blocks of thought itself, whether it's happening in silicon or inside our own skulls.
So, right at the bottom of it all, you've got the transistor. You can think of it as the atom of modern electronics. It's just a tiny, microscopic on-off switch. And what's fascinating is that a ton of early research went into figuring out how even the tiniest little variations in these switches could have these huge ripple effects on a chip's performance. It's a great reminder that even at the smallest scale, little details matter a lot.
Okay, now this is where things get really cool. You take that basic switch, the transistor, and you put them together to build something called a CMOS neuron. CMOS is just a standard tech they use to make chips, nothing too crazy. So you're literally building an artificial brain cell out of silicon. And then you just do what nature does. You link them up to create a neural network, a circuit that can actually start to compute, to think. It's just an incredible parallel to how our own brains are built. And look, this isn't just a bunch of theory on a whiteboard. It's been tested. Get this. With a network of just 2 of these artificial neurons, 2, they were able to perfectly simulate that electrical spiking that you see in a living brain. They even built a real one on a physical breadboard just to prove the concept wasn't a fluke and that it works in the real world. All right, so we've got our basic thinking circuit. Awesome. But, a brain in a jar is kind of useless, right? It needs eyes and ears to do anything meaningful. So the next big step is figuring out how these circuits can actually sense and track what's happening in reality. And this is a perfect way to think about it. On one side, you've got your brain, taking in sound waves and turning them into words you understand. Simple enough. On the other side, you've got an artificial network doing basically the same thing. But instead of understanding speech, it's listening to a bunch of microphones to figure out exactly where a foghorn is at sea. It's the same game. Turn raw, messy data into something you can actually use. Let's stick with this ship for a second, because it's a brilliant example of a complex system. To really model that ship, you can't just listen for the foghorn. You've got to see, right? You need to feel the engine's heat. You need to know about other boats, birds, things under the water, everything. And maybe the most complex part of all, you've got people on board. The captain, the passengers, they're part of the system too. So this is where we zoom in again. We've got the ship as a system, but every single person on that ship, they're a whole other incredibly complex system unto themselves. I mean, think about it. Their heart's beating, they're breathing, all these thousands of automatic processes are just running in the background constantly. So how do you track all that stuff without wiring someone up like a science experiment? Well, that's where something called non-invasive monitoring comes into play. The big idea is you can use sensors, say a thermal camera, to watch someone's vitals, like they're breathing, without ever even touching them. Yeah, I know, it sounds like something out of a spy movie, but the way it works is actually pretty simple. When you breathe in, the air cools down your nostrils just a tiny bit. When you breathe out, warm air from your lungs heats them back up. A really sensitive thermal camera can see that little flicker of temperature change, and boom, it's mapping your entire breathing cycle. Now, tracking one person's breath is cool. Tracking a ship is cool. But what if you want to track lots of things at once? Well, that's where these super advanced models come in. You see these complicated names, but they're basically just really smart ways to track all sorts of stuff. Birds, planes, cars, you name it. It's all about filtering out the static and locking onto the important signal. Okay, let's just take a beat and think about how far we've come. We started with a single switch. That became a neuron. The neuron became part of a person. That person got on a ship. Now we're about to do the final zoom out, the big one. We're going from one ship on the ocean to the entire planet, modeling all of humanity. 8 billion people. I mean, just let that number sink in for a second. That's 8 billion unique,
complex, thinking, breathing systems all running around on this planet at the same time. How on earth do you even start to model that?
Well, here's an idea that just completely blew my mind. What if you took every single person on Earth and represented them as a single dot? If you put all those dots in a grid, just a millimeter apart, all 8 billion of us would fit inside a box that's about 2 meters or 6.5 feet on each side. You could literally put it in your living room and walk around it. All of a sudden, that impossible number becomes manageable, something you can actually see.
But why? Why do this? What's the point? It's about seeing the big picture. It's about understanding the collective result of 8 billion individual decisions. If we can model that, we can make way better predictions about, well, pretty much everything. Public health, the economy, climate science, you name it.
And that's what brings it all back to the start. The whole idea is to stop putting things in separate little boxes. Health tech over here, navigation over there, brain science way over in another building. No, it's all just different views of the same fundamental thing. Complex, dynamic systems interacting with each other. It's one unified reality.
So we've gone on this wild ride, from a single silicon switch all the way up to the entire planet. It gives us this incredible new lens to see the world. But it also leaves you with this one kind of spooky question, right? If we can model a brain, and we can hook that model up to a real body or a robot, what happens when you can't tell the difference anymore? When that line between life and machine just disappears? That's where things are heading, and it really makes you wonder, what's the next step going to look like?